Okay. It's recording, so we have to be quiet for now. Okay, so as usual, this is informal and so on. So this, I started thinking about it because I was asked to review a paper about realizability for non-static analysis. Just a reminder that this is a fun thing. It's quite a classical thing, not very constructive. So I just have to, I mean, I can't stop myself from pointing out when I use classical things, but I will use classical things. So I think we have to live with that. There are certain results, like certain things in non-static analysis we have can't do constructively. So, okay, but what am I talking about? So let's start with piano arithmetic. I guess right as PA. So this is a first order theory of the natural numbers. And so we have something like 0, successor, plus, times, maybe an order relation. So that's our signature. These are the things we can talk about, and then we have certain axioms. So we know that 0 is not a successor, and we know that x is always smaller than the successor of x, and so on. And then the important axiom is the induction axiom, which says that if you can prove phi of 0, and you can prove phi of
and it's the ghost of 1415.
So here I mean universally quantified x, right? But here I'm saying that for all x, phi of x implies phi of sec of x, then I know for all x, phi of x. And because this is a first order theory, I have to do this for every formula phi. So it's a schema of axioms. It's not the second order theory, it's just the axioms. Okay, and then because you have this induction axiom which says that if you know something for 0 and for successors, given that you can only assume it for x, you could think that, well, this is clearly a theory about the natural numbers as we know them. You could try and prove that PA proves for all x, x is factor k of 0 for some k, right? So every x is of this form, so it's 0 or it's 1 or it's 2 or it's 3 and so on, right? And well, how would you prove it? Well, you do it by induction. This axiom, so clearly 0 is such to the 0 of 0. And if x is such to the k of 0, then sec of x is sec of the k of 1 or 0, right? 0 done. But what's the problem with this proof?
How is sec to the k?
Indeed. So I can tell you what sec to the k is.
And how do we even quantify what is k? Like k is being quantified over, so what is it?
Yeah. So okay, so you could allow me to say when I say some k, I could write that as exists.
Yeah, it looks like we have quantification of the numbers. So that's what we don't have is any iteration principle. We have an induction scheme which talks about propositions.
Yeah. But here, this formula here, so the problem
is k plus 0.
When
we have plus, so we can say sec to the k of 0 is k plus 0.
Yeah. Yes.
That's not quite the same thing. It's not saying it's make you stuck.
Yeah, so here I'm really trying to say that this is a numeral, it's really a zero. But the problem is that x equals something decay of 0. It's not one. Because the constructive, like Connor said, have to do a different thing for every k. Could do it for every internal k, but then this would basically be it. And why is it actually a problem? The problem is that in fact, are non-standard models.
So you could say x equals sum of y for some y, right? But that is-
Yes, but that's not very.
It's already
Instructive.
it's already a step.
Yes, okay, so every x is either 0 or a successor, that's true, yes. But there are these so-called non-standard models. And infinite elements. Greater than set of k of 0. Of course, here I'm cheating, but I say for all k, I mean the external k, right?
Because like even if you add in recursion, you still have the problem.
Yeah,
Let's suggest that K might be.
k might be non-standard itself, right? And k could be infinite. Okay, so how would you prove this? So that's the idea. I want to give you two ideas on how you can prove this. And one's going to be more or less syntactic, the other one's going to be more or less semantic. In case you don't like syntactic things very much. So let's start with the syntactic thing.
This takes sharing to a whole new level.
Sometimes the sharing technique is your own punishment.
More than one chair.
Okay, so let me just recall some things very briefly. So we have the soundness theorem or the soundness property.
That's what they call it.
So soundness says that if something is provable, that is true in every model. And by provable here, I mean here I have a set of formulas, and this means I have a proof of this formula, where at the leaves I can have some of these formulas. And the semantic notion here, model, says that every model which makes all of these formulas true will also make this formula true. So soundness says that I have a sensible proof system. It doesn't really matter what the proof system is, but if it's not sound, then there's no point in even considering.
But that is very powerful.
Right. And completeness, which is there to rule out Clement's powerful system, is the other way around, right? It says that if something is true in every model, then it is also proven. Completeness is usually not very constructive, but surprising perhaps. But I think it's actually provable that you can't prove completeness completely constructively. So it implies something like some Boolean primary difference like this. So this is much stronger, right? So if someone tells you that it's true in every model, you have to somehow come up with a proof. This thing you can do by induction on the proofs. That's easy, but say you have an implication into something initial rather than out of something initial. That's much harder. Okay, and then what is compactness? With the compactness theorem, says that if some set of formulas gamma has a model, so gamma has a model if and only if every finite subset some set of formulas that I would like to have a model. And this theorem says that it's enough to take an arbitrary finite subset of this and make a model to that. So this is now not hard to prove if you're classical enough. So if gamma has a model, then clearly every finite subset of gamma also has a model. Because to be a model of this means that every formula here has to be true in the model, right? So this direction is direct. The other direction is indirect. Because we prove this using classical logic now. So assume that it's not true. So assume that gamma does not have a model. Okay, for a convection. And then, of course, gamma models implies bottom semantic is true, because what does this say? It says that every model that makes this true should also make false true. But there are no models that make this true because gamma by assumption hasn't. So by completeness, we know that actually gamma proves bottom, but any reasonable proof system is going to be finite. Right? With this proprietary logic. So I mean that imagine it's a kind of natural deduction system where I have a tree and at the leaves I have the assumptions, and it's going to be a finite tree.
So very access finite subset. We can only access finite.
Yeah, so it can only access the finite subset gamma. It proves finite.
Contiguities.
But
So contiguities.
yes, so I mean the compactness, you can put a certain topology on formulas, and then this compactness here is exactly saying that you know compactness into okay, so let me finish this. Proof of finite. So in fact, there is some gamma theory. Just look at all the leaves of this proof, but telling you about this finite gamma zero that proves bottom.
I mean, this sometimes is called in
What's that?
that thing that you can. I mean, the
Yeah.
property of the illusion.
Yes. Yeah. Yes. So you find this finite subset that proves bottom, and then by soundness. Gamma zero, and actually semantically implies bottom, which is a contradiction to the fact that every finite subset has a bottom. Because clearly this cannot have one. So hence our assumption here must be wrong, and we have not and gamma.
Yeah, there's also a proof that looks more constructive, where you actually take the models of the finite subsets, you can but then you still use a Boolean process filter. So
yes, I mean it is a syntactic approach, which goes via the proof system. But you could say that it's a bit unsatisfying because the statement of the theorem says nothing whatsoever about proofs. Right? So, I mean, you could say that it's very clever to go via this syntactic characterization of what it means to be true or not. But
It's extremely clever to have a complete proof system.
yes. But you could also say there's a bit of a distraction. So you could introduce this way and construct a model directly. Which we'll talk about later. But okay, so that's the compactness theorem. And now, in particular, if we take gamma to be everything that PA proves, And we also take the formula that C is greater than sac to the k of 0 for every meta k. Now there's no problem anymore here because I have this infinite set of formulas, right? But each single formula is just very concrete to say that C is greater than 0, C is greater than 1, C is greater than 2, and so on. And I do this for a new symbol C. Okay, and then by compactness, I can find a model for this if and only if I can find a model for an arbitrary finite subset. But it's again no problem to find a model for an arbitrary finite subset of this, because that finite subset will only have finitely many constraints like this. And I can just take my favorite model of PA, the natural numbers, and interpret C as a +1 or whatever. I mean, if I have constraints that C is greater than 3, 5, and 7, then I can interpret C as so this define any finite subsets. Gamma has a model. Okay, so what model is this? Well, it's by construction, it's a model of PA, but it's also a model where you have this infinite elemency, which shows that we have no Foucault proving this particular proof. Okay. So the reason that this is possible in some sense is exactly because we are restricting to first order formulas, right? If you move to second order logic, then you can instantiate this induction axiom with an arbitrary subset as your phi, and then you're kind of leaking the meta into the object language, and this doesn't work. So it's in a way it's a bad of first order logic that we have these models. On the other hand, it's kind of cool that you can do it, right? And I'll show some examples at the end where I think you can actually do something useful with this. But that's the syntactic approach. Let's now take a semantic approach. Oh, yeah, I'll jump in there. Because exactly like Ezra said, you could try to just take all of these little models here and somehow glue them together into a big model for this. And that's basically what this is doing. But we're going to do it for the special case where every model is the same rather than trying to prove the factness. So the overall idea is to interpret numbers sequences. So this down here is the sequences, this down here is the underlying model. So then we can get the standard numbers. Just constant sequences. But we also get these infinite numbers. For example, the sequence 1, 2, 3, and so on. Because this sequence is eventually going to be greater than every standard number. So you go ahead. And then if you just go along with this for the time being, then you can define operations pointwise. Then to do the plus of two sequences, you have to do it for each index and so on. But there is a problem, which is that if you want this to still be a model of PA, then PA proves that if x times y equals 0, then either x equals 0 or y equals 0, right? And there's nothing classical about this. There are no zero devices in the natural numbers. But in this new model so far, you could, for example, take the sequence 1, 0, 1, 0, and so on, and take that times the sequence 0, 1, 0, 1, and so on. And then this was defined pointwise. This is 1 times 0, it's 0, and then it's 0 times 1, which is 0, and it's 1 times 0, which is 0, and so on. And this was how we define 0, right? So we do have 0 devices in this model. So we can't, if we just take this as our model, then we're not actually validating PA, right? So we fail in that sense. So the solution is quotient. Yes, suitably, yeah. So we get the quotient, so we can't, what we're going to do is we're going to force one of these to become 0. And the classical thing that seeps in is that I can't really tell you which one it is. It's going to be one of them, but since I don't have a constructor way to quote this, I don't know which one.
But why don't you insist on the sequence being increasing?
So I could, but I want to have, okay, so you could say weekly increasing.
Yeah.
It still wouldn't be enough. I mean, this would be fine.
But
Yeah.
maybe not in the rest.
But not for the rest of it, yeah.
I think we proved that like the set of naturals are discrete in the beginning. So there isn't really anything strictly between 3 and 4 EPA already. So, but you do have like a sequence which in this is 3 and a sequence which is 4, so that would be between them.
Right, yeah, yeah.
So this kind of witnesses.
What's the order?
Right, so yeah, a priori, I don't know what the order is. I guess that's not the problem. I will, once you quotient, you can tell what the order is going to be. Because you're going to say that.
Actually, you don't know what the order is because the order is expressible in PA with just addition. But
Right, okay, yeah. Yes, I can define the order as x is more than y. Just very such that x was
Okay, so that's everywhere small.
right, and then in PA you can prove that this is the original.
Second use of it.
And
The second use of doing that right.
right, but I think in this structure it would be total for the reason that you said that's you have these jumps. The things that are not comparable. Everything is comparable pointwise. Whatever you need to do to make this problem go away. So I'm going to tell you what it means now, and it's going to look a little bit like I'm pulling it up to the hat, but I think it is exactly what you need to do in order to really get the property that you still validate PA. And so we're going to define what an ultrafilter is. So first of all, let me tell you what a filter is. You're laughing.
Doing this.
So a filter on some set I is a set of subsets of I. It's a collection of subsets such that first of all the whole set is in the filter. So I'm thinking of this filter as a collection of the big sets. So the whole set is big. Second condition says that we are upwards closed. So X is in F, and if X is a subset of Y, then also Y is in F. So if X is big, then anything that's bigger than X is also big. And finally, the third condition says that we are closed under intersection. So they are big, there's only missing out small things. Right? So if I take the intersection of two big things, I'm still only missing out a little bit. X and Y and F. X intersect one is in F. So thinking of things in the filter as the things that are true in some sense. So the whole set, this is like saying we have everything which is true. It's like we're closed under, and we monotone upwards the trueness. Okay, and then the thing that makes things work classically is that we say that the filter F is an ultra filter. If X is in F for the complement of X is in F, but not both. X. So X is really deciding if X is true or if not X is true. So maybe we should have an example. Best example I can give you is a shear filter. So here we take all the X that are co-finite. By co-finite, I mean that the complement of X is finite. So you're only allowed to leave out a finite number of things from the set. So let's check that this is a filter quickly. If I have the whole set, then the complement of this is going to be empty, which is finite. If I have something which is cofinite, and then I have something which is even bigger, so X is leaving out a finite number of things, then Y is going to leave out also a finite number of things. Could leave out fewer, but it's certainly not going to leave out more. So Y is also cofinite. And if I have two cofinite things and I take the intersection, then they are still only going to miss finite number of things. Yeah. So that's a filter, but it's usually not an ultra filter. For example, if you take all the odd numbers, no, that's not right, is it? You take everything but 0, 1, I take everything. Yeah, we take the odd numbers, then that's not cofinite, but the complement of the odd numbers, the even numbers, is also not cofinite. think is not a filter if and only if by itself is finite. Okay, but the problem was that if we want to interpret classical logic, then we really need this property so we have X or not X, right? So we need an ultra filter in order to do this. So here's the non-constructive step. Really non-constructive because using the axiom of choice in the form of Stone's lemma. So Stone's lemma says you can extend things to maximal fix. Very roughly. And the way we're going to do it is we're going to extend any filter to an ultra filter. So every filter is contained. And you can prove that constructing these ultra filters is inherently non-constructive. If you can do this, then it gets just like Stone's lemma is inherently non-constructive. If you have it. So if you now take U to be ultra filter extending here. We start with these cofinite things that we know what they are. We do a magical thing to make it into an ultra filter. And then we can construct a model that we construct. And the sequences represented by being in this ultra filter. What do I mean by this? So mean that M says that two sequences are equal if the set of indices where they agree is in the ultra filter. So you think of this as being big and containing almost everything. We say that F and E are equal if they are equal almost everywhere. There's only a finite number of places that it is to be.
On that.
Yes, on M. Yeah. And similarly, they say that F is smaller than G, if and only F. The set of indices where F of I is smaller than G of I is. So all the atomic formulas to say it is true if the set of indices where it's true is in the filter. Okay, and then prove. I think now you're well constructed because you've done your magic trick already. And prove. No, I don't think it's true. This model validates all of Peano arithmetic and has non-standard elements. It's exactly this quotient of 1, 2. And the key step in the proof is called Morse's theorem on the population. It says that something is true in the model, possibly with some parameters A, so these are sequences, right? This is true in the model if and only if the set of indices where it is true is in the filter. So this was the definition for atomic formula, and the figure of extent fits to all formulas by induction.
Yeah, is this one constructively valid or do you use choice here?
No, I think you do use choice of
And you also put a very,
Yeah,
very little.
because you have to, when you go one way, you have to actually construct the whole sequence of the tables. Just knowing that it's true that it is. Trust with this choice. So yeah, that wasn't perfect. But many instances are.
You said the algebra power was the.
Yeah. Yes.
Oh, yeah, of course, because if your models are actually the natural numbers, then you could choose the smallest with them.
Ah. Yeah, I guess you could. Yeah, right. I think yes, I think you're right. I think if you have a countable index, that might be okay, but in general, it's equations.
Yeah.
Right.
It's misspelled Borsches, you know.
Yeah, there should be
An accent will be yes.
And wait. Okay. So the nice thing with this is that I mean, even though the rest is non-constructive step in the middle, and maybe even the proof here, at least it's a model you can touch, right? And you know what the elements are, even though it might be fortunate a little bit, but you can actually manipulate the sequences, and you know what the infinite element is. For the syntactic proof, yes, was something that was impossible to not exist by the compactness theorem. But here you at least know where it's coming from. It feels a little bit more constructive, more down to earth in some sense. Because it was alive, it was used as much more but for the final bit, I wanted to Bob was asking me in the list if I meant talk about non-standard analysis and non-standard arithmetic. And now I'm going to talk about non-standard analysis. So far I've talked about non-standard arithmetic. So it's arithmetic as in the real arithmetic, and this analysis as in real analysis. Because everything we've done here, it was a bit confusing before when we had n to the n, and this was the original model, and this was just the indexing set, right? But anything we do, we can replace with some other favorite model to start with, such as real numbers. So let's just repeat this. R3n quotient by our culture filter. These are called the hypergroups. Because anything we did before didn't really care about what the underlying model was. So using the same Borch's theorem, again, and the so-called transfer principle, which says that something is true in the original model if and only if the corresponding thing is true in the extended model. By the corresponding thing, I mean that if this was, so now if I'm talking about reals, I would also like to talk about natural numbers as a subset of reals. So like I have two sorts. So if I have something which says for all x in n over here, then the corresponding start statement says for every hypernatural number. Right? So the non-standard model corresponding to mathematics is non-standard model as well. basically this is what we had before saying that the original model satisfies PA, so the extended model satisfies corresponding statement. But just like before, we have infinite elements, right? So if I call this omega, for example, I have the same infinite elements as before, 1, 2, 3, and so on. But now, if I'm talking about real numbers, I also have division, right? So before I only had multiplication. So if I now have this infinite element omega, which was greater than every k, so now because I have the same ordinary statements being true, I know that because R is a field, I know that the hyperreals is also a field, right? So I know that I have 1 over omega, and I have 1 over k. And if omega is greater than k, then by the theory of the ordinary reals, I know that 1 over omega is smaller than 1 over k. So in fact, 1 over omega is smaller than every standard real number. So 1 over omega is an infinitesimal, something which is not 0, but is still smaller than every standard number. So infinite elements comes. We didn't see that for the natural numbers because we didn't have 1 over. But here for the reals, it makes sense. So we can define epsilon is infinitesimal, if the absolute value of epsilon is smaller than r for all standard. So now I'm working completely semantically, so I don't need to worry about talking about standard elements and so on. It's just something I define in my model. It's not a statement I can define inside the language of the reals, for example, which is referring to standard, right? But it makes perfect sense once I've constructed this model. And then I can also say that x and y are infinitely close, right, like this, if x minus y is infinitesimal. So if x is equal to y, then x minus y is going to be 0, which is going to be smaller than every non-zero thing. So equal things are infinitely close, but I could also have other things that are infinitely close, even though they're not actually equal. And the nice thing now is that you can prove some theorems that look like the kind of thing you might hope for before you know that infinitesimals are a dream that can't exist. So for example, if you take function, just the reals to the reals, and you can say that this function is continuous, by which I mean for every epsilon there exists a delta, such blah blah blah. If and only if x being infinitely close to y implies that f of x is infinitely close to f of y. What do I mean by this? Here I'm starting to talk about things in the extended models. I mean the point-wise extension. So continuous epsilon delta definition is the same thing as just preserving being infinitely close. So with this definition, it's suppose obvious that the composite of two continuous functions is continuous, right? It's just preservation of equivalence relation. With this definition, you have to do a bunch of manipulations to choose epsilon to be the original epsilon divided by 2 to get this rate. But if you have this theorem, you do that manipulation once, and then you can just work with this notion which applies it. In the same way, you can say that the function is differentiable if it pointwise. Let me think of that. Okay, x. If and only if there exists b, so this is the derivative, such that if I now take x plus an infinitesimal minus f of x divided by f of infinitesimal, and that is infinitely close to b for every infinitesimal. Non-zero. So you take the ordinary definition, but rather than talking about the limit of these things as epsilon goes to 0 and so on, you just do it for every infinitely close thing. And then it's not so hard to show that if you are differentiable, then you're continuous and so on. It's just using this definition. And the final thing I wanted to
That's an extension here.
yes, yes. Basically, insert the stars wherever you need to make it make sense. So the final thing I wanted to show was that if you have a sequence with numbers, then we have this sequence converges to some limit L if and only if you take the extension of the sequence and you plug in an infinite natural number, that is infinitely close to it. Again, over here in the standard world, you have to do an epsilon delta argument to say that if you choose epsilon, so for every epsilon, you can choose a little n that's big enough so that you're close enough to L. And here you just plug in something infinite, and you have to be close to value, right? And you prove this using the transfer principle and juggling so you can fix the epsilon before you go over, and then you transfer, and then you transfer back, and so on. I think we're running out of time, so I can't actually show this. So it's always a bit. I mean, these are like theorems, right? But people doing non-standard analysis, that they really, I think that they don't quite trust themselves to get work in this world. So you want to have standard concepts so that you know you're doing something sensible. Whereas if you were really brave, you could just work with these notions, right? And try to redevelop all of analysis just using this infinitesimal notion. But now really backed up by something formal and not the contradictions that we had at the beginning. But that was one of the motivations for developing non-standard analysis. There's some controversies where someone on a journal someone submitted proof of a new theorem using non-standard methods to a journal in real analysis, and then the editor didn't accept it until he had reproved it himself using standard methods. It's like this. So it used to be a controversial subject, but I think it's a nice idea. And you could think why we don't have all of this for type theory. And I think maybe it's because type theory is a little more like second order logic, when you don't have a schema of induction, for example. You really just happy to instantiate predicates. And also you're happy to work inside one theory all the time, whereas first order logic, the syntax is so poor that you can naturally drawn to the models, just working with the models. In type theory, you're quite happy to just work inside the theory. Only reach for the models when you want to show that something is not possible, or you want to justify something. But most of the time, we're perfectly happy as working in Agda.
So transfer the remainder files from formulas first order.
Yes, yes.
It's got to do topology.
And it has to be a formula that makes sense. So you can't mention standardness, for example.
Yeah.
Because this shows that standardness is not definable as well. It was, and then we should give that.
Yeah, so you can't do topology.
So you can't do it on it, yes. But you can do this, right? You can construct this model, and then you can just happily work in this model and do topology in this model.
Yeah.
Which is kind of an experience of doing.
But it was the first one you transfer it back.
Yeah. Yeah, so a lot of the tricks for proving, I mean, it's not hard. A lot of the tricks is just to write this as a first order formula, epsilon and delta and so on.
Yeah.
And then you transfer and you instantiate the epsilon with something infinite. You derive some small consequences of this, and then you transfer back in the end state. Yeah.
How do limits work in hyperreals then? Because you say, oh, the sequence goes to some limit L. What does that even mean? Because you can't say like for every epsilon.
Right. So here, over here, I'm in the standard one, right? So when I say limits, I really mean
Also, yeah.
for every epsilon exists some such that if n is greater than m, then the distance between s and then is smaller than epsilon.
Right. But like this doesn't make any sense in hyperreals because I don't think you like. I think the only convergent sequences are the ones that are eventually constant.
I mean, if I change this to be the hyperlink,
Yeah.
right? Yeah.
So maybe I might be wrong about that, but that's sort of what it feels like.
Well, I mean, you still have all of the old sequences. You still have all of the
Yes, but
the standard sequences.
Yeah, but those aren't necessarily convergent anymore because, like, you get closer than all of the 1/n's, but there are of course many hyperreals which are smaller than all of the 1/n's. So you're not necessarily smaller than all the epsilon.
Right.
N's, but then the same thing would work anyway, because if you at some point you just become L plus epsilon for some fixed epsilon. Of course, you shouldn't go to L, you should go to L plus epsilon.
Yeah, but I think you should still phrase the notional limit using standard natural numbers and standard real numbers and so on, right?
Yeah, all right, of course, then, yeah, you're right, and limits are inherently already higher order, so.
Yeah. But yeah, if you just take this formula and transfer it, then of course you will get the fixed page. If you don't go back.
There's no first order formula.
Yeah. We're quantifying over these elements.
No,
No, well, that's not this. It's the first order formula.
Well, if Sn is sort of a like defined by
Right, I see that. Yeah, okay, so Sn is not standard, then of course this is not standard. Yeah.
Right. But that's only expressible using the language.
Of the original real numbers.
Yeah.
Yeah, then
Yeah.
it's okay. Yeah.
And just real lesson is the sort of kind of trick based on the fact that first order logic won't say very much.
Yeah, you think so, but on the other hand, this, I mean, yeah, I think if you only see the syntactic proof, then that's the conclusion. But I think here you see that there is something semantic going on.
No, but I mean, what I mean is still first order things can't access this extra stuff. So there's a bit of a break, so that it's not like you move to the larger world and then things completely weird. It's we stay within the same language, so you the external things to get more
Right, yes,
The things inside.
yeah, yeah, so
We're talking about it.
that's the amazing thing, yes. But it's still, even if you think that's a bug, right? You're still led to these new models that have interesting consequences. Even if you don't care about language. Still an interesting model.
Look at yours, something else, this is right. 17th century mathematicians.
Yeah, some people don't want to say this.
So use the same word.
Well, that's because the new people have reused the word.
Yeah.
But they didn't mean like some ultra
No,
power,
no,
right?
no, I mean, not the reading.
Yeah, but they meant some, you know, some more like syntactic proof theoretic version of this, right?
I think that it did mean the things on the right.
Yeah, but they didn't.
They just axiomatized it when it turned out to not be a consistent axiomatization.
Well, right. Well,
Right, okay, yeah, okay, they didn't axiomatize it either. Informally axiomatized.
You can also use like whole numbers. Which have similar.
Right. Mhm.
They don't like material. Yeah. That's where some infinitesimal, which is non-zero, but it's very zero.
Right.
Then you cover a lot of like differentiation things as well.
Yes, you get some weird things in the like look at x squared. You
And f(x) is epsilon
yeah.
is x squared plus.
Epsilon is infinitesimal, this is infinitesimal, this is infinitesimal. I mean, effective standard, but epsilon is infinitesimal. This is it looks like this, right? But if both x and epsilon are non-standard, it is something like two which is not infinitely close to 100 squared. So this function is continuous for standard x, but it's not continuous necessarily for non-standard.
That looks like a bug.
It's a very simple function.
Like polynomials should be continuous, right? If your
Yeah.
polynomials aren't continuous, what's going on?
Well, I mean, it is continuous over here in this standard world. It's just the extension. I mean, I guess it's similar to what you said before about sequences. The non-standard sequences are not necessarily well behaved.
Yeah.
Okay, have I lost everyone online?
One question, and maybe that was already asked, so can you do this further, like with hyperrealism? Or is there some reason why that converges? I mean, maybe it's just silly to think about it.
No. Guess you could, right?
But there might be isomorphic.
Yeah, that's indeed what the question is convergent.
And you have infinitesimal decimals.
Then
Not zero, but they're smaller than mere infinitesimals.
we get the identity to be not continuously one.
I don't immediately see why it should converge.
I think they might be isomorphic because what you might be getting is kind of you might be able to join it up into some like you might be so you have the natural numbers twice and like two ultra filters. You might be able to combine them into some those are spare natural numbers, which I mean.
mean, it's making me think of kind of, sometimes you get away with it, correspondence between informal uses of infinity or infinitesimal, that turn into formalizable games with the devil.
Yeah.
Provided you're careful about polarities. I'm thinking of the clock examples, where if you've got a clock functor, and you know that something works for all clock functors, you can instantiate that variable with the identity functor, even though the identity functor is not a clock, provided you use it only in strictly positive positions. Because if it's used in strictly positive positions, you say, well, we're only ever waiting for it. Nothing ever relies on this clock being slow. So you doesn't make it.
More is the same that was just formula is limited in such orders, so you can't make statements which don't distinguish between standard and non-standard variable. You can't distinguish between the time going forward of that. So it really is the limited language that you have. Structure making statements. To express it. And yeah. So make sure. Because we might have it's the same as like if you were careful about your interfaces and change.
Yeah, I was about to say it's something smelling of parametricity as well.
Yeah.
Can't
Detect.
can't abuse it, and it's fine.
I know Jacques Fleury, the way he uses was formalizing ultimately, but and